So let's apply all this knowledge to things that we've already discovered here. So we might be able to use the fact that Earth's gravity, it's at a constant acceleration of negative 32 feet per second, neglecting air resistance. So we might be asked, well, if a ball is thrown upward at an initial velocity of 60 feet per second from a height of 6 feet, how high will that ball go? Seems like a strange question until we realize that we've actually seen something like this before. We found that if we were given the position of a function over time, and we were given a free fall equation, something like s of t, and we found that when we took the derivative with respect to time, we got an instantaneous rate of change of that position function, s prime of t, and that was our velocity equation, right? So the velocity, which was the rate of change, instantaneous rate of change of our position function, right? That gave us our velocity function. And not only that, but if we found the rate of change, the instantaneous rate of change of our velocity before, when we talked about this, that would give us our acceleration with respect to time. Now, our acceleration then is the first derivative of our velocity function, whatever it is, and we might also say that it's the second derivative of our position function with respect to time. So, if we reverse the process, then our velocity function should logically be the antiderivative of our acceleration function with respect to time t. And that's where this is going to be useful, right? Because now we know that if it's constant acceleration, we're taking the antiderivative of the constant negative 32 dt, and that results in a function of negative 32 t plus some constant of integration right here. Well, what could we say about that constant of integration? Well, we know that we've got an initial velocity of 60 feet per second. When we say something like initial velocity, that means what is the velocity at time t equals 0 seconds. So when we say initial, that's an initial condition. And so at time t equals 0, we're told that the ball will be traveling exactly 60 feet per second. And that's when t is equal to 0. So our constant acceleration right here turns out to be our initial velocity, or v0. And so that's 60 feet per second. And our velocity function, v of t, we now know to look like negative 32 times t plus our constant of 60 feet per second. Well, that's nice, because we also now know that if we take the antiderivative of our velocity function, we should end up with our position function. So if we want to find out what our free fall position function is going to look like, we need to take the antiderivative of our velocity function v of t. So I'll do that right here. Let's take the antiderivative of our function right there of negative 32t plus 60 dt. All right, so rewriting this, that's the same thing as negative 32 times 1/2 t squared. That's negative 16 times t squared, plus the antiderivative of a 60 dt, so that's 60 times t, plus, again, we have another constant of integration. I'll call it constant 2. We'll call this constant 1 just for making sure we keep them separate. So there's our function for our position, but there's a little bit more right here because we're told that initially the ball is being thrown upward from a height of 6 feet. which means that at time t equals 0, our initial condition tells us that 6 feet will be the product of negative 16 times 0 squared plus 60 times 0 plus our constant. And so our constant of integration right here is 6 feet. That's our initial position. And so we have a position function that tells us S of t is going to equal negative 16t squared plus 60 times t plus 6. All right, but then we're asked this question, well, how high will the ball go? Well, we know that what's going to happen right here in our free fall equation is that if we initially throw that ball upward, it's going to reach a point where we stop going upward and start going downward, and that only happens at a point where the velocity is equal to 0. So let's go right here. We ask, well, where does v equal 0? Where is that velocity going to happen? So we're going to set our velocity equation equal to 0 to find that. Negative 32t plus 60 is set equal to 0. And of course, solving for t ends up with the number 15/8. When I reduce that, 15/8 is the same thing as 1.875 seconds. So just shy of 2 seconds, we're going to reach the top of that arc. So if we want to find our position, how high the ball will go, that means we have to find our position at 15/8 seconds. So I've done that, and I've worked this one out. And by substituting in 15/8 into my equation, I found that our ball is going to be as high as 237 divided by 2, or approximately 118.5 feet above the ground. And that's how high our ball is going to go based on our initial conditions.